Hello there, Mr. Sutton here with the AB Calculus 5-6 classwork solutions on trapezoidal rule. For this problem, we want the trapezoidal approximation of the area under this curve. Since we're going from -4 to 4 with 4 subintervals, we'll start at -4 and we'll go by 2's. That'll give us -2, 0, 2, and 4 for the other x values. And now we need to get the y values that go with those. Plugging in -4, that's 16 over 2, which is 8. Plus 4 plus 1 is going to be 13. Plugging in -2, that's 4 over 2, which is going to be 2 plus another 2 plus a 1 is 5. Plug in 0, we've got 1. Plug in 2, that's going to be 2 minus 2, which is 0, plus 1 is 1. And then we're going to have 4 plugged in, so that's going to be, 8 minus 4 plus 1 is going to be 5. So doing our first area, we've got 13 plus 5 over 2 times a base of 2. So the approximation from -4 to 4 is approximately equal to this, plus 5 plus 1 over 2 times a base of 2, plus 1 plus 1 over 2 times a base of 2, plus 1 plus 5 over 2 times a base of 2. Simplifying all this, we've got all these 2's canceling, so this is going to be 18 plus 6 plus 2 plus 6. That's going to be, 24, 26, 32. On this problem, we want to find the trapezoidal approximation of this integral using this table. So this is going to be, 0 plus -1 over 2 times a base of 3. And this is approximately equals all of this here. Then -1 plus 0 over 2 times a base of 1. 0 plus 1 over 2 times a base of 3. And 1 plus 0 over 2 times a base of 1. So this is going to be, -0.5 times 3 is -1.5. This is -0.5. This is going to be a positive 1.5. And then this will be positive 0.5. So we've got a negative and positive 0.5, a negative positive 1.5. That all cancels out to give us 0. On this problem, we want to approximate the integral from 0 to 13 of f of x using this table. So trapezoidal approximation, we've got 7 plus 9 over 2 times a base of 3. Then we've got 9 plus 8 over 2 times a base of 5. 8 plus 6 over 2 times a base of 1. 6 plus 4 over 2 times a base of 3. And 4 plus 2 over 2 times a base of 1. Simplifying a little bit more here, this is going to be, 8 times 3 is 24. This is going to be 17 over 2. That's going to be 8.5 times 5. That's going to be 42.5. Then this is going to be 7. This over here is going to be, 5 times 3 is 15. And over here we've got 3. So we've got 24. I'm just going to add everything except this decimal first. So we've got 24 plus 7 is 31, plus 15 is going to be 46, plus 3 is 49. Now we'll add this in here. That's going to be 91.5. Yep, there we go. On this problem, we want to determine if approximating this integral with the trapezoidal rule will give us an under or over estimate. So for that, we need to figure out the concavity of this function over the interval from 3 to 8, and that'll tell us which way the trapezoidal rule is going to go. So first derivative, we've got -3x squared plus 6x. Then we need another derivative. That's going to be -6x plus 6. And out of this, let's figure out critical values. I mean, we could test something in here, but how do we know if that's the case for the whole interval? So if we set this equal to 0 and solve, I can take out a -6. That leaves me with x minus 1, which means I have a critical value at x equals 1. Now, 1 is not on the interval from 3 to 8, so that means that whatever I test between 3 and 8 is going to represent that whole interval. So if I test, for example, 4 or anything else in there and plug that into this function, that's going to give me a negative result, which means that this function is going to be concave down, which means trapezoidal rule under approximates that. For this problem, if three equal subdivisions of -4 to 2 are used, what's the trapezoidal approximation of this integral? Okay, so let's set up our table. We're going from -4 to 2 in 3 steps, so we're going by 2's. We've got -4, -2, 0, and 2 for our x values. Let's get the y values that go with that. So this is going to be, let's see, e to the 4th over 2, and then e squared over 2. This is e to the 0 over 2, which is 1/2. And we've also got e to the -2 over 2. Now it's time to set up some area formulas using trapezoids. So we're going to have e to the 4th over 2 plus e squared over 2 times a base of 2. So there's a lot of 2's involved here. And again, we're approximating. This is not the exact value of the integral. Next, we've got e squared over 2 plus e to the 0 over 2, all of that over 2, times a base of 2. And then we've got e to the 0 over 2 plus e to the -2 over 2, all of that over 2, times a base of 2. Okay, now these 2's are going to cancel out, so if you're thinking this is kind of ugly looking, fear not. We're going to be left with e to the 4th over 2 plus e squared over 2 for that first fraction. Then we've got plus e squared over 2 plus e to the 0 over 2, and then e to the 0 over 2 plus e to the -2 over 2. So at this point, it's all about collecting terms and making it look like one of these answer choices. So one thing we can definitely do is factor out a 1/2 from all of this stuff. And another thing we can do is combine some of these things. So we're going to have a 1/2 parentheses e to the 4th plus, we've got 2 of these e squareds plus 2 of these e to the 0's plus e to the -2. And that actually is one of the answer choices. That's going to be choice E. On this problem, we're looking for a trapezoidal approximation of the integral from 2 to 8 of f of x, and we're given this table to help us out here. So using some trapezoids, we've got 10 plus 30 over 2 times a base of 3 for the first trapezoid. Then we've got 30 plus 40 over 2 times a base of 2. And then finally 40 plus 20 over 2 times a base of 1. Simplifying these, this is going to be, let's see, 40 over 2 is 20 times 3 is 60. Then we've got these 2's canceling, so this is just 70. And then we've got 60 over 2, which is 30. So this adds up to a grand total of 160, choice C. For this one, we have a tank that contains 50 liters of oil at time 4. And then oil is being pumped in the tank at a rate of R of t, and R of t is measured in liters per hour. We've got some selected values of R of t shown in the table above. We want to use a right-Riemann sum with 3 subintervals in data from the table to approximate the number of liters of oil that are in the tank from at time t equals 15 hours. So the key on this one to getting this problem is you have to recognize that in order to find the number of liters of oil pumped in the tank between times 4 and 15, you need to take the integral of this function here. Now what's going on essentially, these y values here are in liters per hour. These are heights, and if you multiply those heights times the base, which is in hours, you've got liters per hour times hours. The hours are canceling, leaving you with just liters. So we've got an integral we need to take from 4 to 15 of R of t, and we also can't forget about the 50 liters of oil that are in there in the beginning at t equals 4 hours. So we've got 50 plus integral from 4 to 15 of R of t dt. So this is going to approximately equal 50 plus, and now they said they want us to use a right Riemann sum. So we have to use all the right endpoints here. We're going to have a base of 3 times 6.2, and then a base of 5 times 5.9, and then a base of 3 times 5.6. Now on this one, this was a no calculator question, believe it or not, so just watch your arithmetic here. We've got 50 plus 3 times 6.2. So 3 times 6.2, that's going to be 18.6. Next, we've got 5 times 5.9. Well, 5 times 6 would be 30, so this is just going to be 5 times 0.1 less than that, so 29.5. And then here we've got 3 times 5.6. 3 times 5 is 15. 3 times 0.6 is 1.8, so that's 16.8 total. Now we have to add all this together. So let me add my whole numbers first. 15, 18 is 68, plus 29 is going to be, let's see, that's almost 98. It's going to be 97. And then this is going to be 113. Plus, now we have to do the decimals. We've got, let's see, 1.1, so that's 114.1, plus another 8 is 114.9, giving us answer choice C. For this problem, we're trying to figure out which of these methods of approximating this area is going to give us an underestimate. So you can do this just by knowing about increasing, decreasing, and concavity with these different methods. We know with LRAM, increasing functions get underestimated, and with RRAM, we're overestimating increasing functions. We know that with a concave down function, trapezoidal method underestimates that. You also could just draw these things out. So here's an LRAM kind of rectangle with the left endpoint touching the function, and we see that there's this empty space that we're not taking into account. So again, that's an underestimate. RRAM rectangle, we'll draw one of those. That's where your right endpoint is touching the function. So this is overestimating. We've got this space that's not under the function that we're including. And then for trapezoidal sum, if we draw one of those, we clearly see that we're leaving out this space in between here. So that's also an underestimate. So that gives us options 1 and 3. So choice D is our best answer. For this problem, we have a graph of a function shown from 0 to 3, and we want to know which of the following has the least value. So key things to pick up on with this graph is that we have a decreasing function that is concave down. Because we're talking about all different types of RAM and trapezoidal sum, so that always depends on whether you're increasing, decreasing, and concave up or down. All right, so let's look at each of these. This first one is the integral from 1 to 3 of f of x dx. So this is the true area under the curve from 1 to 3. So let's see if there's anything that underestimates that true area. Clearly anything that overestimates the true area is not going to be our answer because we're looking for the least value. Next we have LRAM from 1 to 3. Since this is a decreasing function, LRAM is going to overestimate this. So that means that LRAM can't be the answer to this. It's not going to give us the least value. Next, we've got RRAM. RRAM underestimates a decreasing function. So RRAM is actually our winner right now. But let's look at these other options and see if there's anything better. A midpoint sum, MRAM. MRAM might underestimate or overestimate. It's kind of ambiguous which way it's going to go until you actually compare it to the true value, which is kind of hard to do in this case. But even if it is an underestimate, it's not going to be as much of an underestimate as RRAM is. So we can eliminate choice D because it's just not going to be as good as RRAM if it does underestimate. All right, next one, trapezoidal sum. Now, since this is a concave down function, trapezoidal sum will underestimate it. However, a trapezoid is going to fit this curve better with the same number of subintervals than rectangles do. So this is going to be less of an underestimate than RRAM. So RRAM then, choice C, is our best answer.